Welcome back to continuous exponential growth and decay. All right, so this is when we have continuous exponential growth and decay, E is the base. How will you know that this is continuous exponential growth and decay? You're going to see the words continuous or continuously. Right? That's going to tell you. Right, so we have this, and this is in your notes. Right, so N of t, right, and N of t is just the quantity after time t, just like f of t. This one was N of t. By the way, it doesn't have to be N of t. I could have chosen, we could choose any letter we want, right? I just happen to choose N, right? N to represent. What matters is the rest of the equation. So if I have N of t, I'm going to have that N with that little 0 at the bottom. That means N naught, right? And N naught, it just means your initial quantity, right? It's a fancy way to say initial quantity. And then we're going to have E, because E is the base for exponential, continuous exponential growth and decay. And it's going to be raised to the kt power. The k is a constant that's analogous to the growth or decay constant. It's always written as a decimal. And it's either going to be positive or negative. Right? And you'll know what value is k because either it's going to say k equals or it's going to say percent. Right? So k is often given as a percent, and you're just going to change it to a decimal. Right? And that k is an exponent on E. It's positive if it's growth, it's negative if it's decay, right? And t is time. Right? So we're going to be raising E to the kt power, right? Where k is the percent growth or decay, and t is time. Right? So they all follow the same kind of format. They're not too hard really to set up. You got two equations. That's it. You're going to plug in initial, and you're going to plug in the k and the time. All right, and so these are in your notes, and then I've also added some that were missing for decay from your notes as a little addendum. It was just a half a sheet. All right, so certain bacteria, given a favorable condition, grow continuously. There's that word. Soon as you see grow continuously, right, that means E is the base, is the first thing you know, and k is positive because it's growth. The E, because it's continuous. This part here is because E is the base is because it's continuous. K is positive is because it's growth. At a rate of 4.6% a day, there's our percent. That's our what we're growing. Rate of 4.6%. All right, so that's our K. Oops, I was trying to move my line, not my words. There we go. Now I went too far. Stay. All right, so this is K. All right, and I was truly trying to write it above. There we go. And so we need to write that as a percent. So if what we have is 4.6%, that means K is going to move the decimal place 2 times, 0.046. That's K. Find the bacterial population after 36 hours if the initial population was 250 bacteria. Right? 250 is our N naught. That's our starting value. What's our time? Is it 36 hours? No, because our rate here is day. Right? So a little hint here, I'll put it over here. Make sure the units for the equation match the time units you evaluate at. All right? We need to change 36 hours. All right? So T here, we can't use 36 hours. How many days is that? Well, 24 hours is a day. Where should I put this? I don't want to put it by t. Here, we'll put it over here. All right, so if 24 hours is a day, we'd have 12 hours left over. 12 hours is how much of a day? 12 hours is half a day. So 36 hours is 1.5 days. All right, so make sure you change that so they match. Doesn't come up a lot, but just make sure that whatever your rate is, whatever time unit that is, that whatever you plug in to evaluate matches. If it doesn't match, change what you're evaluating at. You can't change the rate, right? That rate is per day. We can't change that. But you can change 36 hours to 1.5 days. Let's put a unit there. All right, so let's write our equation right up here. That's the format. All right, so N of t is equal to our starting value, which is 250, times e to the 0.046 t. Right? And we are specifically looking at 1.5 days. And by the way, let's change that. We can't use a mixed number. Right? So make that 1.5. Or you can make it 3 halves. But since we already have a decimal there, let's make that 1.5. So we're going to plug in for t. Right? So so the top equation is for any amount of time. For 1.5 days, that would be 250 e to the 0.046 times 1.5. Right? It makes no sense to use 3 halves since we already have 1 decimal. Now what you're going to do is you're going to take e. Right? So e, by the way, is located where it says natural log. And my calculator, first I have to turn it back on because it went to sleep. I'm going to do second, and then where it says natural log, that gives me e to the x. And then you should see a parentheses if you try it. You're going to plug in the 0.046, and then you're going to plug in times 1.5. Don't forget to close your parentheses. Some calculators will know you meant to close the parentheses, but some calculators will get confused. Just close the parentheses, no big deal. All right, and that's going to give you e raised to that power. Just take that, multiply by 250, and you got your answer. So this was growth. We expected a number greater than 250, and we did. 1.5 days is not a long amount of time. So you got 859 bacteria. That's how many bacteria we'd have. All right. They're not growing too fast. This was only a day and a half. Let's try another one. Continuously, see, there's that word, and growing, that means K is positive. Bacterial population has a growth rate of K equals 0.05. All right, so now they already told us what K is. Sometimes they'll be nice and do that for you. You don't have to do anything to it. That's one thing with these problems. You don't add 1 to it. You just use K just the way it is. All right, so I'm going to put a little reminder there. Don't add 1 for E as a base. It's different, right? Because it's an exponent. It's not our base. It's an exponent on E. E as a base. All right, so just add that to your notes. All right. And initially contains, initially contains, that's our starting value. There's 100 individuals, 100 little bacterium. Assuming time t is measured in days and that the population follows an exponential growth function, how many individuals are in the population after 5 days? This time it matches. Right? Our equation's in days, and we want to know after 5 days. Right? So no need to change there. Right? So the amount after any number of days would be 100 times e to the 0.05 t power. If we want to know the amount for 5 days, we're just going to replace t with a 5, and now it becomes a calculator problem. All right, so we have, all right, so I'm going to do second in natural log. That gives me e, and that's because natural log and e are inverses of one another, so they're on the same button. 0.05 times 5, I'm going to close my parentheses, and I'm going to multiply that by 100. Or I can move a decimal place, 2 points. So that's going to be 128 0.403. All right, not much time, so but we did grow a little bit. Let's look at the last problem there. The 1980 population of the United States was approximately 231 million, and the population has been growing continuously, right? So that means E is the base, at a rate of 1.03% per year. Predict the population in the year 2011 if this growth trend continues. I've been using this question for a while, so now it's no longer a prediction, but let's say this is now 1980, all right? So we have N is our starting. So 231 million needs to be changed to a number there, and a number not in words, right? So a million is going to give it 6 zeros. The first 3 are for the hundreds, the next 3 are for the thousands, and then we have the millions. K, we just need to change that percent, right? So we have 1.03%. Move the decimal place 2 places to the left. That's going to be 0.0103, because 1% like a penny, right? 0.0103. Our time is, so in the year 2011. So our equation is in years, so we have no problem with the units. And 2011 will be 20 years to get to 2000, and another 11 years means 31 years. Okay? So the amount for any amount of time is 231 and then 6 zeros, E to the 0.0103 t power, right? And we want to know for 31 years, that's going to be 231 million e to the 0.0103 times 31. Oh, close my parentheses there. And now it is a calculator problem. Well, we're at the end of the page here. All right, so I got to type in a lot of numbers though. So I got second natural log, it gives me E. So then we have 0.0103 times, and then 31, close the parentheses, and that is, and then we're going to multiply that times 231, and then 6 zeros. So our population would be 317, I think it's 317 million. That's where all the numbers in, and then I'll 317, then 893, and then 909.9. All right, so if you wanted to round to the nearest person, you probably would round up one more. So we have 317,893,910 people. Okay? That's a lot of people. All right, so this is continuous exponential growth. We also have continuous exponential decay. And the next problem is on that little addendum. All right, so because I had very few decay problems. They just got left off. And I wanted us to practice some decay. So radioactive Skittles decay continuously at a rate of 8.1% per hour. All right, so we see continuously, that means that E is the base. And I should probably write another color, huh? 8.1% per hour, all right? So a rate of 8.1% per hour. That is our rate of, since it's decay, decrease, so it's going to be negative, all right, because it's decay, all right? So K is negative. So we have, since it's 8.1%, we're going to move it over, and we're going to make it negative. Move the decimal place over 2 places. So it's going to be negative 0.081. There are 5,000 radioactive Skittles. That's our starting amount. how many radioactive Skittles will be left after 1 day? All right, so T is not 1 because it's percent per hour. So we need to, got to watch for that. It doesn't happen a lot, like I said, but just make sure those match and then change the day to hours. And how many hours in a day? There are 24 hours. All right, so any amount, the amount after any time is going to be 5,000 times e to the negative 0.081 t power. We want to know specifically for 24 hours. And because our k is negative, and this is decay, we're going to have sorry, a smaller number. I was trying not to sneeze, but I was not successful. So the amount after 24 hours is, all right, let's plug this into a calculator. And by the way, the work that you see me write, that's all you need to write. For the evaluating, you're going to use a calculator. Can you imagine how long you'd be trying to figure this out without a calculator? You'd be, and because e is a irrational number, it never ends. All right, so oops, can't forget the negative. Negative 0.081 times 24, and then times 5,000. We have 715. Boy, that's a lot of decay. 715.6514. So I'll just go to 3 decimal places. I usually use 3 or 4 decimal places. I'll go 4 here. 6.6514 radioactive Skittles. That's how many are left. Not too many after a day. You got a good chance of getting a good one. There's over 4,000 good Skittles there. It might take a chance that you don't get one of the 715 radioactive ones. All right, let's solve a couple more problems, or evaluate a couple more problems. And these are also in that addendum. A rabbit population of 200 grows continuously at a rate of 15% per year. All right, as soon as we see grows continuously, the continuously part means E is the base, and growth means this is going to be a positive number, and this is per year. How many rabbits will there be in 15 years? No problem with time here, right? They're in the same unit. Our starting amount is 200 little bunnies. The K is going to be positive because it's growth, so we have 15%, and that as a decimal would be 0.15. The time is 15 years, right? So we have NT, any amount. The amount after any time is 200 times e to the 0.15 t power. And we specifically want to know for 15 years. So 200 times e to the 0.15 times 15 means we have how many bunnies? So we have, let's see, 200. Oops, let me do the e first. All right. Oops. I personally like to just take care of e and then just multiply it by the starting amount, especially when I'm holding a calculator with 2 fingers. 0.15 times 15, close my parentheses, equals, and then times 200 is, we have 1,897.547 bunnies or rabbits. All right, so that 200 becomes 1,897. All right, not as much as when we had the growth of 75%. That was a lot of bunnies. This one's not as much, just growing continuously, but it's only 15%. A radioactive material decays at a rate of 1.5% a minute. How much would be left after 1 hour if there's initially 2,000 grams? All right, so let's look for all important words. And, well, I left off an important word. So let's add it. Continuously. All right, so this isn't going to be continuous exponential growth and decay unless we see the word continuous. And I meant to put in the word continuously. So somehow it got lost. So let's add continuously. So a radioactive material decays continuously at a rate of 1.5% per minute. How much would be left after 1 hour if there's initially 2,000 grams? All right, so our starting amount, there is initially 2,000 grams. So 2,000 is the starting amount. All right, we have 1.5%, but it is decay. So that means K here is going to be negative. Right, so when it's decay, K is negative. When it is growth, K is positive. All right, so we have K is going to be 0.015, and time is, so our rate here is decay per minute. And we want 1 hour, right? So we have to change that. 1 hour is 60 minutes. We can't use 1, right? Otherwise, it'll be wrong, right? Because we won't have calculated for an hour. We will have calculated out for a minute, right? So the amount after any time is going to be 2,000 times e to the, whoops, I put decay, and what happened to my negative sign there? 2,000 times e to the negative 0.015 t power. And then we want to know for 60 minutes, so that's 2,000 times, whoops, and somehow we got 20,000. There we go. 2,000 times e, and then we have negative 0.015 times 60, and then let's calculate out how much is left after 60 minutes. So let's see. We got second, whoops, hit the wrong thing, second natural log, and then we have negative 0.015 times 60, close my parentheses, and then multiply that times 2,000. There's going to be 813.1393 grams. And you can measure parts of a gram. If you wanted to round up to 1,898 bunnies, but I usually like to just go to 3 decimal places, right? Because so you can be a little bit more exact. Where are you on that? Let me just double check that, right? Make sure. And yeah, it's 1.5%. That appears to be correct. I just double check, make sure it wasn't 15%. All right, so there we've done some continuous growth, some continuous decay. We're going to do one more application of continuous growth. I, in that addendum, gave you this formula here. I haven't just written down the formula, but decided to give you the whole spiel so that the formula would make more sense for you. And that's on the addendum. You don't have to write anything down. I cut and paste the entire thing. All right, so continuous compound interest. All right, so now if we're dealing with compound interest, there is no decay. Right? This is just a application of continuous growth. Right? So continuous compound interest, A equals PE to the RT, is really the same thing as N of T equals N naught E to the KT, except they use letters that go more with money and money earning interest. That's all, but it's the exact same thing. All right, so R is the same thing as K, P is the same thing as N naught, all right? A is the same thing as, it's your accumulated amount. It's the same thing as N of T. R is your interest in decimal form, so these R instead of K, so it goes better with interest. And T is number of years. And this is always years. Right? There might be an application where it's not years. None of what we're going to be working with is anything but years, because that's the most common use. So if interest is compounded all the time, it's going to use the word continuously. We'll use the formula above. It's the exact thing as continuous growth. It just has words that match money better. That's all. It really wouldn't matter if you used the n of t equals n naught e to the kt. All right, be the same thing. All right, so let's let's evaluate a few of these with some money. Vera has placed $1,200, $1,200 in a bank savings account. By the way, this one's not in your notes, which pays interest compounded continuously at a rate of 7.5%. How much money will be in Vera's account? All right, so the present amount, right, what does she have now? She has $1,200. The annual interest rate is 7.5%. And the total time period is 20 years. All right? So we're going to find out how much money Vera has in 20 years. We'll just plug in everything. All right, so we have 1,200 times E. The 7.5% is going to be changed to 0.075. We're just going to move that decimal place 2 places. So we have 1,200 E to the 0.075. And if we have T, actually I'll pull in T. That will tell us for any number of years. We're specifically going to look at 20 years. So that would be 12,000 E to the 0.075 times 20th power. And how much money does Vera have? She has, let's see, a second. Yeah, E up already. 0.075 times 20. And then take that and multiply by 12,000. She'll have $5,378. We'll always round this to the nearest cent. And 3 cents, because it's 0.026. Not bad, because Vera didn't do anything. Her money did all the work. All right, let's evaluate another one. All right, I think I've got 3 here, and I have just 1 that's in your notes. Now she's got $19,500. Vera's got a little bit more money. The interest rate is 8%. All right, so that means R is going to be 0.08. And the total time period is 6 years. She's keeping it a little longer. That's a pretty good interest rate. So A of T equals 19,500 E to the 0.08. Let's write that better. 0.08. I want to find out how much money Vera has after 6 years. And Vera's going to have, let's find out. So 0.08. Second, E. Now 0.08 times 6. And we'll multiply that times 19,500. That's going to give us a grand total of $31,513.45. And that's pretty good because, again, the money did all the work and Vera did nothing. And she has not doubled her money, but increased it by quite a bit. One last problem, and this one is in your notes. Let's come on. Any day now. Any day now. Last one. Suppose you deposit $1,600 in an account paying 7% annual interest compounded continuously. And by the way, it'll always be annual interest. Otherwise, you're dealing with a loan shark. If you're owing the money, it's a loan shark. And if they're giving you the money, wow, that's pretty good. But it's always going to be annual. Find the percent after 15 years and round to the nearest cent. Right? And you have this one in your notes, and you have the formula A equals PE to the RT. Right? A is the amount that we're going to have. Right? That's our accumulated amount. P is our principal or balance that we have right now. And that is, we've got $1,600. R, right, is our interest rate as a decimal. So if it's 7%, that means it's 0.07. We will never work with the percent. Right? And time is 15 years. All right? This will always be years. All right, so we have on the amount is, and I'm going to make the A of t because we want to show how many years we're evaluating for. So A of t equals 1,600 E 0.07 t power. And we want to know for 15 years, right, so that's going to be, right, so let's evaluate that. So we have second, and so we got 0.07 times 15, and then multiply that times 1,600 gives us 4,572.24. Pretty good. All right. So here in this lesson, we evaluated and found out how much we had or how many there were for a certain amount of time. In the next lesson, we are going to figure out how long it would take to get to a certain amount or to have a certain number of rabbits or awesome toads or money. All right, so stay tuned for that lesson. Bye for now.